Welcome back to our lesson in nomenclature. And before we begin, I want to make sure that you have the right tools. What we have out in front of us is our note pack. And let me just kind of bring up my image of the note pack. The last time we were together, we had just finished talking about how atoms arrange themselves on the periodic table and had drawn some practice models of phosphorus and potassium. The next blank spot we have is actually on the bottom of page 5. So before you begin listening to this video instruction, be sure that you are on the bottom of page 5 of our note pack. And another good tool to have out is our periodic table. All right, so our periodic table along with the bottom of page 5 in the note pack. And what we'll continue to do then is pull up our PowerPoint and begin talking about some words. The next step of our journey is to start taking atoms, which are very unstable in their electron arrangement, and putting them together to create compounds we call compounds are ionic or compounds are molecular. And the first part of our journey of nomenclature, learning the language of chemistry, will be creating ionic compounds. So we just have to focus on one category first, then the other. Let's take the time to write in our note pack the following vocabulary words. The first of our terms is called an ion. An ion are charged atoms. Remember, to a chemist, we only care about electrons in terms of an ordinary chemical change. It's the electrons, and more specifically, the electrons in the outermost energy level, that a chemist needs to keep track of. And the outermost electron energy level allows a chemist to predict things such as reactivity, physical characteristics, properties, and how it bonds to create a compound. Atoms are unstable in their arrangement. Every atom has an envy of the noble gases because of their full electron in the outermost energy level arrangement. And atoms are going to do whatever it takes to become like a noble gas. They will either lose electrons, gain electrons, or share electrons with other atoms to become more stable, like the noble gas. So as we begin talking about ions, these are atoms that, in order to become more stable, have either lost or gained electrons. A type of ion known as a cation is called a cation because it is positive. To help me remember that cations are positive, I notice the little positive sign right in the term cation. Cations are positive ions because they have lost electrons. Sometimes that confuses a beginning chemistry student. But if I model that, let's say with a simple atom such as lithium. Lithium, who is number 3 on the periodic table, mass number 7, just reminding us of standard notation. Draw with me, remember. Draw on these extra notes so I know you're watching the video. That would tell me there's 3 positive protons in the nucleus, and there are 4 neutral neutrons with an electron arrangement of 2 and then 1 electron. In a neutral atom, atoms are neutral, ions are charged. That's a big step forward. Atoms are neutral, that the positive protons do indeed equal the negative electrons. But that's not the case here any longer when an atom forms an ion. Remember, every atom wants to become like a noble gas. If lithium can lose an electron, now it's going somewhere, someone else wants to hook to lithium and take that electron from it and form a compound. But if we lose an electron, we still have 3 positive protons, but now we only have 2 negative electrons. 3 positives and 2 electron negatives give me a resulting charge of a positive 1. The atom of lithium is neutral. The ion of lithium carries a +1 charge by losing an electron. Remember, there's an unneutralized proton
unaccounted for by an electron. Loss of an electron is a positive ion. And we literally write that symbol for the lithium ion as Li with a +1 as a superscript up high. Lithium ion carries a +1 charge by a loss of an electron. Please add on the extra note so I know you've been listening to the lesson. Let's talk about anions. Anions, this is my way of remembering that they are negative ions. A negative ion, the A, then the N, in my head reads a negative ion. Anions carry negative charges because they have indeed gained electrons. Now let's model something that might look like that. I'll do a fluorine off our periodic table. Look with me. Fluorine has an atomic number of 9, a mass number of 19. I'll just pick the nearest whole number. There are, of course, a variety of isotopes. Drawing that simple model of fluorine places 9 positive protons. To do the subtraction, 19 minus 9 would give us 10 neutral neutrons, a configuration of 2, then 7 electrons. Right now, this atom is very unstable. It really wants to have a full outer shell. Remember up above lithium? We said it's easier to lose one than try to put 7 in. By losing one, the outermost electron shell becomes full, just like the noble gas helium. Well, with fluorine, do you think it's easier to gain one and become like neon with 10 electrons, or try to erase 7? Lose one, gain one or lose 7? Well, of course, fluorine was going to gain an electron. If we add an extra electron, it had 7. Let's put 8 in the outer shell, giving it 1 extra electron. 9 positive proteins, but 8 and 2 now is 10. If I have 9 positive protons, but 10 electrons, do you see how the resulting charge gives it a -1 overall? When atoms gain electrons, they become more negative. Electron particles are negative. Adding in extra negative particles makes the atom become negative. Those are known as anions. Atoms that lose electrons have unbalanced protons. Loss of an electron creates a positive ion. Cation, see the T? A positive ion. An anion, a negative ion. Loss and gain of electrons. And friends, you can start predicting a beautiful relationship between cations and anions, positive and negative, by the simple law of electricity, opposites attract, that I must have a cation and an anion electrically neutralized to form a compound. And that's the heart of ionic compound chemistry. Certain elements lose electrons, certain elements gain electrons, the heart of forming that beautiful relationship known as ionic bonding. Let's take a peek then at our next slide. Let's model a sodium and a chlorine. Now a sodium and a chlorine, give myself room to draw, makes us flip to the top of our next page. Let's draw simple models of sodium and chlorine. So this is on the top of page 6, really under the number 1 and 2. I'm just going to put them all under the same slide. Alrighty. So first we go to work with a little periodic table skill. Do you see where sodium is? If I just bring up the periodic table quickly, sodium, of course, right here, sodium is number 11, and let's use a mass number of 23 just to draw that simple model. So here's sodium, Na, number 11. And just while we have it up, we'll find chlorine over here, number 17. We'll pick an isotope. Let's pick chlorine 35, and we'll just begin drawing simple models. I have a sodium and a chlorine. Alrighty? So I'm just kind of getting that ready as we begin drawing simple models. Standard notation for sodium would place 23 over 11. Sodium, as a simple model, has 11 positive protons, 12 neutral neutrons, and an electron configuration that places 2 electrons in the first energy level, 8 more electrons in the second energy level, and 1 valence electron in the third energy level. Remember our periodic table skills. We know the meaning of this based on where it lives. We know that because sodium lives in period 3, we knew 3 energy levels. All the elements in period 3 have 3 energy levels. That's why it lives where it lives. We also know that sodium lives in group 1A. That tells me it has 1 valence electron. The electron in the outermost energy level is the term valence. We drew 3 rings with 1 outer electron, 1 valence electron. This is very, very unstable. This outer electron shell is not a completely full shell. Every atom wants to be like a noble gas. Do you think it's easier to try to input 7 more electrons to achieve an outer shell that's full, or might it be easier to lose 1 electron, erasing that entire third energy level? Losing 1 electron makes the second energy level the outermost energy level, and it's a full outer shell. Gain 7 or lose 1? Well, I agree with you. It's easier to lose 1 electron. And that's exactly what sodium will do. It wants to lose this electron. Where would it go? Well, suppose there's another element, like chlorine. And again, just continue drawing a simple model of chlorine. You're kind of putting it down here in step number 2. A simple model of chlorine. Let's start with an atomic number 17, mass number 35. We put mass number over atomic number. It just helps me draw a simple model of a chlorine atom. We would place 17 positive protons. 35 minus 17 gives us 18 neutral neutrons. An electron configuration of 2, 8, 7. Chlorine lives in period 3, 3 energy levels. Chlorine lives in group 7A, 7 valence electrons. The number of energy levels comes from its period. The number of electrons in the outermost level comes from its group number. The representative elements, these group A's, represent their number of outer electrons by what group they live in. Well, right now, I'm noticing this outer electron, this outer energy level, the third ring, is not stable. It isn't full. Remember, every atom wants to have a noble gas arrangement, a full outer energy level. Right now, it only has 7. The third energy level requires 8 to be full. So we have a choice. Do you think it easier to put in 1 electron to complete that outer ring, or to try to lose 7 electrons and erase that whole third energy level? Gain 1 or lose 7? Well, I agree with you. It will most obviously lose, excuse me, I'll start over that. It'll gain that electron to complete the outer shell. And where it will go in is in this third energy level. We will add in the extra electron. Where do you think that would come from? If this wants to gain an electron, where might it come from? And I know you're seeing it. I know you see right here a beautiful relationship forming between a sodium and a chlorine. If sodium wants to lose 1, chlorine wants to gain 1, we start to develop what's called an ionic compound, the loss and gain of electrons. Well, let's see, what would the resulting ion be? If sodium atom loses an electron, it goes to a +1 charge. The sodium now becomes an ion with a +1 charge. I'm going to write that as the Na+1. Now remember, loss of electron creates a cation, a positive ion. The chlorine gained an electron. Gaining an electron produces an anion, a negative ion. The chlorine started neutral, but by putting in an extra electron, it now carries a -1 charge. Sodium was neutral as an atom. By loss of an electron, just one electron is lost. We still had 11 positive protons, but now with losing this electron, we only have 10, giving me a net +1 charge. Chlorine, if we input to create a total of 8, it had 7, but if it now has 8 by adding that electron in, it still had the 17 positive protons, but now a total of 18 electrons. It has a net charge of -1. When I gain electrons, it becomes negative. When I lose electrons, they become positive. And perhaps you can see when a sodium atom bonds to a chlorine atom, forming ions, we create a compound built of ions known as sodium chloride, an electrically neutral compound built from a cation and an anion. Sodium chloride is ordinary table salt. Notice how overall we've built a model that is electrically neutral. Sodium lost 1 to achieve a noble gas. Chlorine took it in to achieve a noble gas. This opposite attraction is known as an ionic bond. Literally, this arrow that we drew a moment ago, if you have drawn in that, let's label that. This is the very definition of an ionic bond, an electron transfer from a metal to a nonmetal. If atoms lose electrons, they go somewhere. They're going to give them to an atom that is looking to gain an electron. We just drew a model of sodium hooking to chlorine. What type of bond did we form? We formed an ionic bond. Ionic bond is an electron transfer. Let me clean up the screen just a bit and show again. Ionic bond when a metal, remember where the metals live to the left, sodium was a metal in our example before, transfers an electron to a nonmetal. That was our chlorine a moment ago in our previous example. An electron transfer is known as the ionic bond. Metals will always lose electrons. Nonmetals will always gain electrons. Metals lose electrons. Nonmetals gain electrons. Metals will become positive, nonmetals will become negatively charged. The type of bond that we just formed, and this is what we're putting in the letter E, all of this that we wrote together, known as an ionic bond, we're defining that in our notes to be an electron transfer from one element to the other. The metal will lose and a nonmetal will gain. Ionic bonds, the transfer of an electron to create an electrically neutral compound. If we continue that thought, we can certainly investigate some other atoms forming ions. If we were to find magnesium on our periodic table, magnesium, right here, number 12 on the periodic table is its atomic number. We can use the most common isotope. We'll round down this time. We'll use the isotope that has a mass of 24. And we'll draw a simple model of magnesium showing how it becomes an ion. So I like to start with the standard notation, 24 over 12. A simple model shows the 12 positive protons inside the nucleus. 24 minus 12 shows the 12 neutral neutrons in the nucleus. Magnesium is period 3, so I now know to draw 3 energy levels. Magnesium lives in group 2A. The A are known as the representative elements. They represent the number of valence electrons. I know it will have 2 electrons in the outermost energy level. 3 energy levels altogether from the period. Group 2A told me the valence electrons. To complete the energy levels, we know they fill with 2 and then 8. And the valence shell is what chemists care about, 2 electrons in the outermost energy level. If the magnesium atom is unstable, it wants to achieve a noble gas arrangement. Here's the choices. To fill the third energy level, up to the 8 it would so desire, one choice is to try to add 6 electrons into the third energy level. Another choice is to remove 2 electrons that are there. Easier to gain 6 or to remove 2? Well, I agree. The outermost energy level, only 2 electrons, is easier to lose those, and if we do, we erase the entire third energy level to where the second energy level, so the loss of 2 electrons, makes the neutral atom of magnesium form an ion of magnesium. The magnesium ion lost 2 electrons. I mean, they're going somewhere. There is an atom out there that is going to bond to magnesium. The 2 electrons don't magically get erased in space. They're traveling to a different element who's looking to achieve a noble gas by gaining electrons. If I lost 2 electrons, it now carries a positive 2 charge. Notice why? We still have 12 positive protons, but now only 10 negatives. A plus 12 and a minus 10 gives me a net positive 2 charge. We've just shown the magnesium ion forming from its electron arrangement using a solar system model, a Bohr model. A magnesium ion loses 2 electrons, developing a plus 2 charge. To say the name of positive ions, we just say the name of the element as is, and we just simply add on the word ion. We drew sodium ion. We drew the chlorine, the 2 positives, sodium ion, magnesium ion. You'll notice that when we drew chlorine to chloride, that we actually have a negative ending there for the chloride. And we'll talk more about the nomenclature, saying the name of the positives as they are, but the negatives we know end with IDE. I'm going to try to just change the layout, give myself some more room to draw here. How would magnesium and chlorine come together to form a bond? So we're going to form a bond between the magnesium and the chlorine. I'm just trying to drag this up and give myself some room here. Well, we drew magnesium a moment ago. We saw that it's going to lose 2 electrons. And again, I'll just quickly draw. For magnesium, that symbol here, Mg, we put 24 over 12, and we could see that it had 12 positive protons with an energy arrangement of 2, 8, and 2. We know that it needs to lose 2 electrons. That's what it needs to do to achieve a noble gas arrangement. Well, remember also from a little while ago, we drew a chlorine. I think I do a 35 over 17. Just to remind ourselves what we drew. We had 17 positive protons in the nucleus there. And we arranged the electrons to have 2, 8, and 7. Chlorine needs to gain 1. Magnesium needs to lose 2. Well, if magnesium needs to lose 2 to achieve its noble gas arrangement, chlorine needs to gain 1, we need to draw in a second model of chlorine. Do that with me. Repeat exactly as we drew so we have a place to drag both of those electrons. Now remind ourselves, these little particles are electrons. Let's just envision what I'm doing here. This number 2 actually represents 2 separate electrons. And with my pen, and you do this as well, I want you to show me that it's almost like a click and drag on our computer screen. If I were to able to just pick this up and transfer it into the first chlorine energy level, this is a transfer of an electron. That's the very definition of an ionic bond. A transfer of an electron from a metal to a nonmetal. That got rid of one of the 2 electrons. It still needs to erase one more. I'm going to take the second electron and give it to the second atom of chlorine. It took 2 chlorines to neutralize electrically the magnesium. Magnesium lost 2 electrons. The name of that ion we said was magnesium ion. A single picture of chlorine turning to an ion gained 1 electron, but we had to draw 2 of them, didn't we? To name the negative ion, the endings change for negatives. Chlorine becomes chloride. The structure we're showing is, for every 1 magnesium, we had to draw 2 chlorines for a place for both of those electrons to go. The overall chemical formula for this ionic compound, for every 1 mg, 1 magnesium, we had to draw 2 ions of chloride. Subscripts tell me how many of each I drew. Our chemical formula for the ionic compound with the name magnesium chloride, MgCl2. Chemical formulas tell us how many of each element there are in a formula or in a compound. 1 ion of magnesium neutralized by 2 ions of chloride. The compound called magnesium chloride. The heart of chemistry, moving electrons around to achieve a noble gas arrangement. When we name positive ions, how do we name them? The positive ions we've been saying. Let's formally write it. We simply say the name of the element with the word ion after it. By saying the name of the ion, we simply write out Mg with a +2 charge. We'd write out Mg +2. Write this with me. We have an Mg with a +2. We just name that as magnesium ion. If we were to name Al with a +3, we just simply name aluminum ion. Say the name of the element with the word ion. What about the negatives? The negative says, let's take the name of the element as written, kind of lop off the last syllable, and change it to IDE. Chlorine becomes chloride. Its symbol is Cl with a -1 charge, gain of 1 electron. Sulfur becomes sulfide, lopping off the last syllable of the element. Sulfide carries a charge. The element sulfur is neutral. The ion sulfide carries a -2 charge. Say the name of the positives just as it is with the word ion after it. Say the names of the negatives but end it with "ide." Little nomenclature. That's what language is in chemistry, nomenclature. How do we say the names? The compounds that we have been forming are commonly called salts, ionic compounds. Ionic compounds are commonly called salts. Ordinary language, most everyday language, a common word I hear is salt. We have table salt, we have rock salt, we have a lot of varieties of salts. I didn't clearly write that very well. An individual building block of an ionic compound called salts are formula units. If I were to build in a three-dimensional crystalline structure a sodium chloride, we start to develop a three-dimensional array of repeating patterns. What I'm trying to draw here is a repeating pattern of a positive, negative, positive, negative, positive, negative. This is really what a crystalline substance looks like. Just this repeating three-dimensional pattern. I screwed up that row. In all directions, I'm building a cube, alternating positive, negative, positive, negative. And that's exactly what these guys do. These are always, always, always solids at room temperature, built of these three-dimensional crystal arrays, just as an ordinary table salt is in a crystal form, like a cube. But if I could go in at the atomic level and see the repeating pattern of the lowest subscript ratio, one chlorine to one sodium, one chlorine to one sodium, over and over and over, that basic building block in the repeating pattern of a larger structure called a crystal is known as the formula unit. Write this with me. The formula unit, the lowest subscript ratio of an ionic compound. The lowest subscript ratio of an ionic compound, commonly called salts. When we wrote NaCl, that's a formula unit, the lowest subscript ratio possible to create a neutral compound. We drew a moment ago MgCl2, magnesium chloride, the lowest subscript ratio possible in a large repeating pattern known as a crystal. A formula unit is the basic building block of a larger crystal array in these properties of salts. When we build ionic compounds, we always build them of ions. Ions come in two flavors, positives and negatives. It makes no sense to hook two negatives. It makes no sense to hook two positives. We hook a positive ion to a negative ion. And by convention, we always, always, always write the positive ion first. Positive first, then the negative, just so we're all doing it in the same way. So we have ions, a positive ion known as a cation, hooked to a negative ion known as an anion. A positive hooked to a negative, so that when we're done writing our formula, we've created an electrically neutral compound. Their charge will add to 0. Metals, we're just beginning this journey. Metals will lose electrons. Metals will always form positive ions. Nonmetals will always gain electrons. Nonmetals will become anions, negative ions. Very quickly by a formula, If I want to know if it's ionic, I see a metal hooked to a nonmetal. That's the guarantee I've identified it to be an ionic compound. Metals are positive, nonmetals are negative, and we'll balance the charges with our subscripts. These are very, very large crystalline structures with a three-dimensional array. Salts are always solids at room temperature. It takes a great degree of heat to get a salt to melt. And if I can just convince you to remember formula units, or another name for a repeating pattern of a salt, we're on our way in nomenclature. Let's review some highlights of our lesson so far. The review. I'll read it. Please follow along. It says, give the name and the symbol of an ion that forms when sulfur gains 2 electrons. Gaining electrons makes it become more negative. What's the symbol for sulfur? Do you see it? Right here. Sulfur. Whoops, I didn't mean to do that. How many electrons would sulfur need to gain to become like a noble gas? Just helping us start predicting. Here's sulfur. It's 2 spots away to become like argon. I bet that it wants to gain 2. And we'll get better at that prediction as we start to think about where atoms live on our periodic table. When sulfur, symbol S, gains 2 electrons, it becomes negatively charged. To name negative ions, we change the last syllable. Sulfur becomes the sulfide ion. Gaining electrons, putting in extra negative pieces makes it become more negative. If the aluminum atom loses 3 electrons, what's the symbol for aluminum? Do you see it? Aluminum is number 13. Its symbol is Al. The story problem told us if it loses 3 electrons, remind yourself, losing makes you become more positive. Aluminum, after it lost 3 electrons that were negative, becomes a +3 charge. And we simply name it the aluminum ion. And if calcium loses 2, oops, I hope you wrote that so you can erase it with me. Loss of our negative electron forms a +2 calcium ion. We have one more review. How many electrons were lost or gained in the following example? All we need to do is look at the charges. A +2 charge means it lost electrons. The name of this would be called the barium ion. As -3. As comes from the element named arsenic. Arsenic in Old Lace, a poison. Arsenic. Notice the -3 charge. It's carrying extra electrons. It has gained 3 negative electrons. Arsenic becomes arsenide. Here's the IDE for the negative. The arsenide ion. Copper, Cu, is now carrying a +2 charge. It lost 2 electrons. This will be known as the copper And I'm going to say it, and I'm just going to let you know this has a Roman numeral associated with its name. And more on this in a minute, but because this is a Group B transition metal, Group Bs, we will learn, not today, but we'll learn that Group Bs must be named with a Roman numeral to tell me the charge on the ion, a copper 2 ion. And I'll just see this a little bit now because the word transition, copper is a shorty in the middle, means it can transition its electrons between orbitals. Sometimes it loses 2, sometimes it loses just 1. It depends on what it's reacting with. It depends upon what it might be bonding with. Copper with a +1 charge would be known as the copper Roman numeral 1 ion. It's these Group Bs we need to elaborate more on coming up in a future lesson. Group Bs transition their electrons. We do not know their charge based on where they live, like the representative elements. Those are easy. So we just let the reader know how many were lost by using a Roman numeral when we name them. That will be practiced a whole bunch more. The last example, S carrying a -2. We see that the negative ion has gained 2 extra electrons. Sulfur becomes the sulfide ion. Friends, you've done good work today. So far, we've reviewed atoms forming ions, and when they do so, many of them will either gain or lose electrons to achieve a noble gas arrangement. And so as we think about how we begin hooking atoms to become ions, we just start to consider what makes them more stable. Well, what makes them most stable is becoming like a noble gas. When they become like a noble gas, they achieve the outer arrangement that's stable. Stop your video here, and you are now ready to begin the homework assignment on ionic compounds.